Hi, I'm Julie Sarama,
I'm Doug Clements.
and we're going to talk about this website called learningtrajectories.org. So, Doug, what is learningtrajectories.org? Why does anyone care?
It's all about learning trajectories. And learning trajectories are important because they're about kids. They're about kids thinking about mathematics. They're about how kids learn mathematics. And they're about helping kids learn mathematics better in an enjoyable, motivating way.
You know, that sounds really exciting to you. It probably sounds really exciting to me, and it probably is exciting to just a few other people that we know that are really excited about how kids learn math. But in terms of, your everyday person, why would they go? What would they find on there that would be particularly helpful?
Oh, what you find is a whole lot of resources. You can read about learning trajectories for different topics, so you find out how kids think and learn. You can explore some online games about it. You can find resources about helping kids who are dual language learners, helping kids in different ways and the like.
So I always talk about learning trajectories, or it reminds me of one of my cooking websites, where if you go to the cooking website and you're looking for something pretty simple, like a way to cook green beans, and you type in green beans in the search, you get so much information it can be a little overwhelming. But the reality is if I'm looking for a lot of ideas for teaching green beans, I'm going to find it. And if I go over here and I click on Explore LTs, indeed, there are learning trajectories for so many topics. And if I click on each of these topics, all the levels. And if I click on either one of these levels, I've got great videos that I can watch to help me understand learning trajectories.
Okay. Mana dia? Good evening, Prof. Douglas. You're in?
Yeah, everything's in and
Nice. Julie's not joining us?
still have to make some adjustments here.
Okay. Go
Get
ahead.
my backlighting on here. There we go. A little more light.
Hey. Oh, ada gitar.
Okay.
I'm just going to try to share.
Recording in progress.
Is that coming through okay for you?
Yep, it is.
Super. So
All right.
I'll stop sharing and I'll start again once we keep going.
Okay. Just give me a few minutes. We will start and sharp at 9.
Bawa tanya gitar apa?
Hmm?
Tanya gitar.
Is that electric guitar or can't hear you? Can't hear you.
Sorry. I played folk guitar in high school, then electrical guitar to pay for my way through college, and then then took up classical. So
I see. So that's classical.
now I just play classical, yeah.
All right.
Or
Okay.
try to.
Is it a comfortable? Was it a comfortable life to play through college with guitar?
It really was. The trouble is you hardly make enough money to get through college even. We weren't exactly raking in dollars.
Yeah, expected.
That's all.
What's your
Pardon?
role? What do you do?
Pardon?
What do you do?
On work-wise?
Yeah, just
No,
in.
okay. But I'm more involved in optics, the
Ah,
research on optics and photonics and stuff. So right now, making my own materials to modify with more towards electro-optics.
that's fascinating.
Bread and butter. Not rocket science yet. Not rocket science yet. Still on the lower levels.
One of our colleague who's in literacy, Nell Duke, um, always tells people that rocket science was way easier than doing education well.
Yes.
You know,
Yes.
at least it follows rules.
My wife is doing something on education, and I look at the stuff that she goes through. It's crazy. And science is technology, science is maths is so much easier, so much more structured. The result is either yes or no. Whereas
Right.
education is so subjective that you just can't put your finger on one thing.
Complex and nuanced. There's a wonderful article by David Berliner a long time ago in a journal, Educational Researcher, entitled Education Research, the Hardest Science of All, by which he means, people say, we're in hard science, so we do actual science, you're in soft science. And he makes the point that hard is also means difficult in English. And he said no physicist would stay in their career if the materials that they were working on and experimenting with decided to get up and walk out of the room at moments.
Exactly. Yeah. Good evening, Julie.
Hello,
Hi. How are you?
I'm good, thank you. Glad to be here.
Nice. You're not in, you're at home?
We are. We're both. We're both. We're both.
Okay.
7 o'clock here, so it's still it's home time. In
Dinner's
fact, we
done?
just ordered Indonesian and Malaysian food for dinner, so to try to get in the spirit of the talk.
It was delicious too, actually. Yeah.
Yeah, it was delicious, except Doug kept going, "It's so hot."
just one of the dishes really knocked me out.
I've been to a few places back in States, and I think you should come over here to try hot. We use those what do you call in Malaysian in Malay we call it chili padi. It's what is birds what do you call bird beak chili. It's just a small 1 cm 5 mm to 8 mm. And that will really
with me I'd be knocked off the chair. It was already pretty hot for me in a regular dish. So
okay. You don't do sriracha?
Yeah, for sure. But this was, I don't know what kind of chilies they use, but I can have sriracha sauce on almost anything. I can handle heat.
Sriracha is okay.
Yeah.
I would say on the lower mid.
Yeah, Yeah, jalapenos are fine. I can eat pickled jalapenos, but
Okay. The jalapenos are okay.
but I do not know what was on the fish, but it definitely was too hot for Doug. So, but it was delicious. We had fish
Okay,
with
okay.
spice. Yeah,
Oh, it was fish. All right.
we got a couple things. We got fish, we got chicken, we got beef.
Okay. All right. That's nice.
Duck
Yeah.
and I think you got tofu too, right? It's tofu
Yeah.
dish.
How much does it cost?
Oh, too much. Yeah, Denver's so pricey for restaurants. It's just ridiculous. So I think it was like I don't know. It's like I'd have to go look, but it was not. Not cheap. But this is a nice place. It's a family-owned place, so I let it go.
Okay. Something with fish. Over here, it will be about 10, 15. Oh, sorry. On a nice upper range restaurant, per person will be about 80 to 90. So that will come up to about just shy of 25 USD.
Oh, okay. That's about similar then. But this is not a super nice restaurant. This is just a middle of the road kind of place.
About there, yeah, about there. About there, yeah. That's nice.
Hmm.
So, you guys were in Denver all the time, or just back from somewhere?
We just came back from Sweden.
So, okay. How long ago?
Sweden was wonderful. We have a great collaboration group there. People from Sweden, Norway, a couple groups from Norway,
Germany.
Germany, Ireland. So just a nice group of people, and we're going to try to do some cross-cultural studies. So I'm hoping we have another meeting on the calendar already, and we can keep this collaboration going. So it was a nice group. Nice to meet with colleagues and not have it just be a presentation, you know.
Okay.
Like to actually sit down and talk and about ideas for, I think, 2.5 days. Usually it's like this. We have a short time to talk and then we're done and we don't see people again. So it was nice to have extended time and really talk to people, and it was fun. Hopefully this could spur somebody. If anyone's interested in collaborating, please reach out. We're
Yes,
happy
yes.
happy to talk. Yeah.
I think we will start about now.
Yeah, that sounds great.
Okay.
Great.
Just give me a few minutes. I'll be back in.
Doug, you ready?
Oh, do you want me to start sharing?
Yeah.
Oh yeah,
Nope.
let me read up the thing. A short welcoming speech.
Yeah,
Okay.
I thought
Okay.
it was an
I'm going in now. Okay. Salam sejahtera, selamat pagi, and a very good morning to all gathered here virtually. We are here for Isaac's 16, thanks to the ever-increasing efforts of Doctors Nazri Halif and Sharifah Nofaiza. Thank you too to UNIMAP Vice Chancellor Prof. Zaliman Sauli and Deputy Vice Chancellor of Research and Innovation Prof. Rizal Fandi, their respective officers and broadcast control team here for hosting this event yet again. And a very good evening to our distinguished presenters, Profs Douglas Clemens and Julie Sarama. Before we hear both of them, please allow me to describe a bit about Prof. Douglas. Julie, I'm sorry I do not have your bio. Douglas H. Clemens, previously a preschool and kindergarten teacher, is a distinguished university professor and Kennedy Endowed Chair at the University of Denver. A researcher and curriculum developer, Dr. Clement's contributions have led to the development of new asset-based mathematics curricula, software, teaching approaches, professional development initiatives, and models of scaling up innovations, each focusing on inclusion and equity. Funded by the Institute of Education Sciences, National Science Foundation, and others, he has published his research in over 185 research studies, 8 books, and 400 additional works. Research and statistics have documented that in the entire field of maths education, Dr. Clements is the first most influential author in the US and second in the world. That's nice. Congratulations, guys. Now, Prof. Douglas and Prof. Julie will enlighten us about the surprising importance of early maths. Profs, the Zoom is all yours. If you don't mind, we will break in anytime to disturb your presentation. Thank you.
We would love it if you put in the chat or just unmute and interrupt if you have questions during. We'd love that. I will start out by saying that Julie, say about what your experiences are, but it's easy to say what Julie has done because everything I've done has been with Julie. So we've been colleagues for decades now, and everything that was academic achievements are equally shared by us too. But Julie, you taught actually senior high.
I was a maths teacher who got interested in early childhood. Doug was an early childhood teacher, got interested in maths, and we've been collaborating for decades.
And we have spent the last, now, Julie, it's 15 years now at least, in this early math, by which we mean birth through about age 7 or 8 years. So what we're going to talk about today is the surprising importance of early math for everyone. So we're going to, the first surprise we're going to talk about is it's surprising how predictive math is of later school success. In the US, in large-scale research, tens of thousands of kids, hundreds and hundreds of teachers, various studies. What they looked at is on the y-axis here is early entering kindergarten, which in the US is somewhere around 5 years of age, entering reading skills, math skills, and then attention skills, internalizing and externalizing problems and social skills. And what you can kind of see here, since this is later school grades, and this is the 0 here, is that these cognitive and social emotional things are not very predictive. It doesn't mean they're not important, but teachers and family work on those pretty effectively so they're not barriers to later school success. Julie and I were really shocked to see that the most predictive factor of these for later school success was early mathematics. And we'll try to make the point that it's not probably that kids knew their numbers and shapes as much as mathematics is a way of thinking and reasoning. Because mathematics done well can do more than just the math content. Math content, really important, but it also develops critical thinking and problem solving, executive function, social emotional competencies, language abilities, and over a lifetime, these and other skills compound, and we all benefit from investing in children's early math learning. So I hope some of you are a bit skeptical. Really, early math gives you all this? I'm not sure I believe it. Well, you can believe it. Thinking skills? Yes. This study right here showed that students who lack math education showed reduced brain levels involved in reasoning and cognitive learning. And Julie, why don't you talk about executive function a little bit?
So we had an idea that if children had higher of executive function, that they would be able to engage in more difficult math activities especially the young, really young children, that if they were too busy doing other things and unable to control themselves, maybe they wouldn't have as much being able to get as much out of the math activities. So what we did is we set up a study where one group of randomly assigned classrooms were given a math intervention. And we, Doug and I, and doctoral students taught teachers about how kids learn math and gave them materials to use and activities to do. And in another group, we taught them how to do math, but we also had a colleague come in and teach them how to support children in their executive functioning. And a third group was just whatever they were doing, you just keep doing it. Well, we went in, we worked with teachers for a year, and the next year we went in and we tested children at the beginning of the year. It took a while to get the pre-tests and then end the year, but it was really only about 6 months time span. And what we were expected, again, was the hypotheses, was that the math children would score higher in math, and that the executive function plus math group would score higher than them in math because they would do more math. But they would also obviously score higher in measures of executive function. But what happened is the math only group scored higher in math and in executive function than the executive function group. We had no executive function intervention. And so what that told us was that engaging, just the act of engaging in meaningful mathematical activities for the children was enough to increase their levels of self-regulation and executive function. And so that pretty much, that study was such a surprising result that just spurred future work on how best to support executive function while teaching math.
So these articles are available, and they're more practically oriented, teacher-oriented articles on how to even better than we knew at that time to support both at the same time. Social emotional, to many people who sat in U.S. classrooms when they were 5, 6, and 7, they would think I just did worksheets by myself. How can that help social emotional? Well, first of all, high quality math involves collaborative thinking, turn taking in games and other things. And then I love this little study that came out in the prestigious journal Child Development. They taught kids to count better and likely fairly. So their sharing was better. Sharing was throughout the day rather than just in terms of, counting out things to share. And math and other content predicts later social emotional growth more than social emotional early competencies predicts later math. So it's really interesting that good content, high quality content that Julie was describing really makes a difference. Julie, I'm going to turn it back to you because this was your study.
When we worked with teachers who were in preschool, so much of their focus, and I'm sure it's similar there, is on literacy. Everybody wants to support literacy. We want children to learn how to read. That's an important goal. Of course we do. And so when we worked with teachers to teach them how to support children learning math, what happened is they got really excited about it and they started seeing math throughout the day and doing much more math. But they were getting nervous. They had a lot of anxiety because they were like, oh no, we're not doing literacy. Our children aren't going to do as well in literacy. And when they go into school and they're not going to know their letters, they're not going to know their sounds, what are they going to do? So after we finished working with them in their preschool years, they started in kindergarten, and we went in and we tested children, and we tested them on, do they know their letter names? Do they know those sounds? Absolutely. The children in the math group did just as well as the children in the regular group. But we also told them a story about a naughty bus and had the children tell us back the story. And then you record those answers and you code it. And the children in the math group gave more information. They used more complex language. They were more independent, meaning they needed fewer prompts to keep going. They just told the whole story. And at the end, they scored higher on those inferential questions. So again, it's one of those nice things that doing a math intervention really helped children's language. But it's not just any math intervention. I just want to be clear here. We don't have children just doing worksheets or writing their numbers. The kind of math intervention that we're talking about, you'll hear more about later, really involves children talking about their thinking. And that's probably why we had such effect, and probably why we have such an effect on self-regulation. Go ahead, Doug.
The teacher's always asking, how do you know? Why do you think that? How did you figure that out? Creativity, again, people who saw mathematics as follow the rules might think you're joking. But no. The implementation of high quality math in this particular study, tangram puzzles, enhanced the overall creativity of first grade students. Again, age is like 6 or 7 in the United States. And they measured that creativity not just with the Torrance test of creative thinking have a verbal component and then kind of more a spatial a component. They got an uptick in creativity on both those measures. And like Julie's already said this, I think, it's high quality math. It's asset based where kids are involved. It's content that's challenging but achievable. Okay, that's surprise number 1. Surprisingly important, surprisingly generative of learning and development. Surprise number 2 is young children in such an environment can learn amazingly broad, complex, and sophisticated mathematics. And then surprise number 3, this is a couple of your books that you worked on here, Julie. Talk about that for us.
Just that we've been able to compile this research on how kids learn math, and there's quite a few large policy documents that indeed recommend the approach that we're going to talk about today for teaching math. A lot of it because of our own research, but the research on our work by other people. In other words, taking what we've done, other people have researched that approach as well. Internationally. And so the results are pretty solid. And so there's lots of documents out saying and policy in the US saying really this is the best way to go. But our stuff is not ours. Our stuff is based on taking everybody's research that we can find on early childhood, synthesizing it, and that's the basis for what we do with children.
Yeah, and I don't know how it is in Malaysia, but in US, we really have a problem with early childhood because we're tending to do better and better in preschool, 4-year-olds, but then kindergarten the next year they take often teaches kids only what they already know. And so you often find the research saying, well, the preschool effects faded, but they don't fade. We were just talking to another researcher who was talking about, no, they don't fade. All her research shows if you keep building these ideas through kindergarten and then primary grades, they maintain. I don't know about, again, if your milieu has discussions of science and teaching. And the unfortunate thing in the United States, and we were just in Australia where this is going on a lot, right, Julie, is that there's groups in these various countries, don't know about yours, who talk about that the science of math is this side of this unfortunate dichotomy between two approaches. Julie, take it away.
What we have, and again, this is shared by our colleagues, so we hope we're this is something similar, something you've heard, is there are people who say, look, it's one or the other. Either you take an inquiry approach or you take a direct, explicit instruction approach. So what does that mean? What does that look like? Well, problem solving. You give a child a problem and you just ask them to solve it, and you don't teach them anything, and the mathematics emerges from the children engaging in the work. The direct explicit instruction people say, no, you watch me do it. I solve the problem. Then we solve the problem together. And then you get do the problem independently and practice it. But it's truly just modeling. Another example is students discover information on themselves without having it presented. That's sort of the model, right? Look, you don't have to teach kids anything. They're going to discover it. It's all going to come from them, as opposed to the idea that no, teachers need to model and explain concepts and skills. Students copy and practice.
Guys, the inquiry-based approach looks quite familiar, like what we practice in maybe a bit in high school in Malaysia, and somewhat in university syllabus. We call it problem-based learning, PBL.
Yeah. Okay. So I that's like a good that is perfect that you just said that, because I'm going to build on that. So on the left side, the inquiry approach is very much PBL on this last thing, where you're going to give a problem and then children share strategies, or high schoolers or college students share strategies, and then through that discussion you come up with, okay, well, here's what we're doing, right? As opposed to, again, a standard algorithm. So for example, the problem on the left, which is pure arithmetic, a child who's really thinking about number would say, well, it's 1,136 because it's 990 is close to 1,000. So I'm going to make it 1,146 and take 10 off. And that's a solid way to do it. But there are plenty of teachers in elementary school who are angry at that, right? They want you to line it up and do it by columns. So as if you're interested in that PBL approach, there you go. Problems elicit the models of thinking, and they're mixed types, as opposed to problem types are taught you do this kind of problem, like a rate problem or a max and min problem. You teach one at a time and kids get good at it, and you review that problem and you move on. The thing is we know as professors, as math teachers or whatever, is that it's not one or the other. That there is a time where you're going to have to kind of explain something, and yet we also want to probably start with kids starting with something and trying to wrestle with the problem and figure it out, and then we come in and it's more of we go back and forth between the two columns. The unfortunate thing that's happening is people are saying, no, pick one, all inquiry based or all modeling, and you can never mix it. And the people who are loudest right now are the people who are saying we're hurting children by letting them start with problems. And so we're trying to say that if you look at the studies, that's not the case. Go ahead, Doug.
No, that's the science of math approach. In Australia, that's led by Sweller and some others who do very interesting research in cognitive load theory, and they use that to say you have to have direct instruction. It's too much for kids to do an inquiry based. I think especially young kids, but they really apply it to everyone. In the United States, they're very sure that it's modeling and practice. And they have their research. You can't read it. I can't even read it on the screen right here. But there's lots of research there. The trouble is there is research supporting explicit instruction, including direct instruction. But in math, most is explicit. Like the National Mathematics Advisory Panel report that I was honored to be on says that explicit instruction has its place, but direct instruction, at least anybody who follows the kind of direct instruction in the United States that came out quite a few decades ago, but is still used, it's very much what Julie just said. I do, we do, you do, and you do it exactly like I say. And the worst thing about that is that they ignore all the other science. So, for example, that they a line from their review of this kind of stuff says that systematic and explicit instruction is identified as research validated practice in mathematics, and there is favorable compared to unassisted discovery learning. And they quote this Alfieri article, which is 2 meta-analyses. And I want to just tell you a little bit about those two, so you can understand my frustration with cherry picking. In other words, choosing the research you want to report on and ignoring the rest. Alfieri did 2 meta-analyses. In the first one, they compared unguided discovery learning, unassisted, unguided, to direct instruction. And they found out, unsurprisingly, that direct instruction performed better. First of all, because the direct instruction directly taught what was on the test that they designed. But secondly, and I think this will impress anyone, this was not an early childhood study, so it was older kids, secondary level children, students, that what the unassisted discovery learning was this. You had a sheet of problems, you passed it out to your class, you left the room, and you come in at the end of class and you score their papers. You can't get more unassisted than that. There was no adult in the room when kids were working, and they weren't talking to each other or working in groups or anything. Not like you were just explaining before about what you do, what was similar to some Malaysia instances. Then, so, okay, it's not a very impressive thing, but it's a true result. What they don't tell you is that the same group in the second part of their article compare guided discovery to direct instruction, and guided discovery performed better. And they just ignore it. And, it's frustrating. That's why Julie and I think that really we need to figure out what's true about a good. So, Julie, we know a lot then, we said, and we think a science of education is more, we encapsulate it as learning trajectories. So do you want to take that away?
Sure. So learning trajectory is a bad name for a pretty simple idea. And we were kind of frustrated with general approaches for how people were approaching. Everyone has a good idea for how to teach kids, and no one was really basing it on the real science. So go ahead, Doug. Advance. Learning trajectory is important, and we consider 3 parts. One are the goals, and that's kind of what most people consider the curriculum. Like, what are the standards where we want children to learn and in any given topic? And the next most important part is, how do children learn that topic? And I'm not talking about how do we break it down into tiny steps. I'm not saying that, if you're going to add fractions, first you get a common denominator, and then in order to do that, you need to find the least common multiple. It's not like that. What we're talking about is, if children were going to learn fractions, how do they understand it? And so we looked at the research, like I said, from developmental psychologists, cognitive psychologists, early childhood researchers, and math ed researchers, took all that and looked at it, and we can come up with, okay, we have a sense that this comes before this for children, from the children's perspective, not from the math perspective, from the children's perspective. That's the developmental progression. And the third thing is, what do we do to help children get there? So the way we talk about it is that if we taught children how to walk the way we teach children math, what we would do is we would say, okay, we all want to be able to walk, and we're all going to teach walking today, and watch me, I'm going to walk. Watch how I walk. watch me, see I'm walking and the children don't do it, we're thinking, ugh, these kids, they're just not good at walking. They're not good walkers. I don't know. Their parents don't do good walking with them. They're not good walkers. When I was a kid, I learned to walk. So then you're going to sit there and you go, okay, I'm going to break it down. You try to tell the kids, okay, first you're going to put your foot down. Maybe you hold their little hands and try to get them to get on walk. Well, if they're babies who are barely sitting up, that makes no sense, right? If they're kids who are already walking, it makes no sense. They're going to run away. And you're going to be like, no, learn how to walk, or else good, you know how to walk, get a gold star and then go play. And then the next day you're going to do something else. And for the kids who are behind, you're just like, ooh, you better catch up. You're going to have to learn how to walk. Maybe the parent should get a tutor and teach you how to walk more. It would be crazy, but that's the way we do with math. And what we try to say is we don't take these hard concepts and break them down for little kids. We pay attention to where the kids are. So when the child who's crawling, who isn't able to pull themselves up yet, we say, wonderful, you know how to crawl. We can work with that. Here's what we're going to do. We're going to put some stuff high, and then maybe you're going to want to pull yourself up. And that's going to help you have a motivation to get up. And I might even help and support you a little bit to stand up. And then you can grab some things and that'll be a good day. That's a good thing. And for the child who's already walking, we're going to put some stuff higher for you and see if you can climb, because we're not going to let you sit still. So what the learning trajectories are is they're asset-based. We're always looking at what children can do, not what they can do. And we want to take those teaching practices and activities and help children move to the next level. Our goals don't change. We want the children to walk, to run, to succeed, right? But the way we approach it changes. And we want to find out what children can do and build on that. That's what learning trajectories are about.
And we've done what we've done.
Allow me to interrupt on that, Julie. Let's say that is the scenario. I don't know how you do it in the States, but here in Malaysia, a whole bunch of students are put in one class. So how is the teacher to, how should I say it, divert attention between crawlers and walkers?
Yeah. I mean, that's a really good question.
More like management problem.
It is a problem, and it's true. In the US, we typically don't have quite as big a class size. But I will say that when I work with teachers of really young kids, yeah, the reason why you have smaller classes for really, really young kids is because the variation is greater. But if you start going into typical school age, what I will do is I'll go into a room full of teachers with various experiences, and I will give a problem like I just gave, 990 plus whatever, 146. And I'll say, okay, everybody, take a minute. I want you to think about how you would do that. Raise your hand, tell me how you did it. And they'll say, okay, here, oh, I got this. Okay, how did you do it? Oh, what I did is I said 990 is close to 1,000. Good. Okay, how did you do it? I looked in my head. You always have one person like that. And I thought 0 plus 6. And they basically are doing it the old way, but in air, right? That's the way, they can't even think about it. And then I'll have somebody else who says, I took 10 off. They do a compensation. So I took 10 off of here, put it here, moved it here. Pretty much you ask, okay, any other ideas? Maybe you get 3 strategies at most in any given room of people. So pretty much, and I will do it again. I'll do it again. Like the next time I'll start a different problem, a geometry thing. I'll do it. How did you do it? You get about 3 different ways. Those 3 ways pretty much follow 3 levels of a learning trajectory pretty similarly. So no matter how big the class is, teachers can kind of have a sense that they're differentiating with 3 levels. Now, are you going to have outliers? Absolutely. You're going to have those little kids who are really just, you have to figure out what to do with them in any case. And you're going to have some kids who maybe have a learning disability or something who are really, really struggling. In which case you want to still meet them where they are, because if you start just trying to like ignore it and just follow me, it's not going to happen. They'll never catch up. They'll just learn to say what to say, but it's built on sand. But the teachers really get it if that usually it falls into about 3 levels. So give a problem, pay attention, and you have to differentiate a little bit higher for some kids and a little bit lower for some other kids, and it usually works. It's not as big a management. It's not like each individual kid has their own trajectory. It pretty much falls off to about 3.
And Julie, they might be working in groups that you kind of arrange so that these different strategies can both be expressed and developed. But I didn't hear you say anything about for early childhood the lack of small group instruction many times.
Yeah, so what we do in early childhood is we do small groups, and they don't do it in upper grades, but we've really seen it be successful with upper grades. Working with a group of 4 or 5 children is as effective as working on tutoring one-on-one. So if you put children in groups and you spend time paying attention to their strategies, and I'm not talking ability grouping, I'm saying just in groups, and you pay attention to what they're doing, it allows you to really see their strategies and build on it. The older they get, the more you can do that in a whole class environment, because children are able to listen to each other, and you get to be a good teacher where you get students to talk to each other, where you become the orchestra leader, right? Oh, how did you do that? This kid's understanding. Oh, I did it this way, where it isn't you as the center of attention. But when they're younger, it's particularly important to put them and have small group time where they're working, and you can ask questions like, how did you do that? What were you thinking? How did you know? That allows you to get more insight into their thinking. My son, our son, sorry, Doug, our son, he loves when I say that. Our son did arithmetic in his head a lot. He's got problems with his hands. He has a lot of pain in his hands. And as a little guy, he just didn't like to write. He still doesn't like to write. And he had to do all his math in his head, fractions, everything. And I remember when they were going to start doing subtraction in 3rd grade, where it was a lot of zeros, right? And I knew that there was going to be a lot of writing, crossing out and doing this. And I thought, this is going to be a disaster for this guy. And his teacher was very strict. That teacher loved her red pen. All she wanted to do was to grade papers. Red was her, just loved it. So I said to him, and talking to him, I just said, so I gave him a couple problems, and I said, how do you do it? And he always went left to right. So if I have, 2,000 minus 500 and something, well, 2,000 minus 500 is 1,500, minus 60 is 1,440, minus 2, 1,400. It's the way he did it. It made sense to him, and then he'd write down the end. And I was like, okay, good. You're going to be okay. You understand. And he went to class, and I was busy, and I didn't pay attention. And I got out my camera because I wanted to take a video of him talking through his strategies. And he took out a pen and was crossing out all the zeros. I said, no. Do it the way you told me in the car. He said, no, I can't. I don't even know I don't remember. I don't do it that way anymore. His teacher had totally like, you will do it my way and my way only. And she lost his reasoning. She never asked children, how did you figure it out? She didn't care. Right? Just follow me. But if you're in a small group setting where there's strategy that matter, I think it helps you be a better teacher, and the differentiation becomes pretty easy. Even what I was just saying, start off with something like 1,000 minus 450, right? You change the numbers slightly for the kids who are struggling, and then make it more difficult for the kids who are doing better. Sometimes the tweak is so small. Go ahead, Doug.
That's great. Same theme, moving a little bit to the focus a little bit. We've done studies because there's many studies. I think we have a slide of all the studies flashing across the screen later on. But many of them confound that the learning trajectories approach compared to a different approach, business as usual or whatever, is confounded by that the learning trajectories approach also is a new curriculum, also has professional development and the like. So we did a series of 10 studies. This was the first one, where we tested the assumption that levels of thinking are best taught consecutively. In other words, that we're going to help that infant raise his head and then roll around and then crawl and then walk, like Julie said, versus teaching the child just the target skill, like having them walk at 3 months or whatever. And what we found is a very clear difference where all the kids learned something, but the kids who were taught with the learning trajectories approach learned far more than the kids who were taught with the teach to target approach. And here's something that to me is still amazing. And we've done this with 10 studies. Not all of them worked out perfectly. I won't go into details of that, but none of them were against learning trajectories. We had methodological problems. But the important thing here is they even perform better on the type of puzzle here, type of problem that this group had spent all the sessions on. So think about that. They spent more sessions on the very problems that were our real test of competence, but the group that came up through their own levels of thinking outperformed them. They also showed less frustration and more engagement, as you can probably imagine. So, Julie, you kind of formed the PD kind of thing. Did you want to talk about what we did and to invent this to teach teachers learning trajectories?
Yeah, what we knew is that teachers, particularly teachers in the early grades, struggled with understanding things by doing a lot of reading. And, the demands of the day are overwhelming, and they're not very comfortable with maths. Most of them go into teaching early grades because they don't like math. They like literacy. And so what we originally wanted was a way to communicate with the teachers about these good activities and about children's development. And the best way to do that is with videos. So we made a website where every activity that we thought was good for a kid was up there with a video. You'd be able to watch a video of a teacher doing it. And then to understand children's development, there were videos of every level of the development. That was all on the website. So that was originally tied to a print curriculum, which then became something that was updated. And now we have our latest version, which is called Learning and Teaching with Learning Trajectories, or LT Squared. And anyone can sign on at learningtrajectories.org or use that QR code right there.
And Julie, we don't have much time, but do you want to try to do a little example with the topic of
Yes. Why don't you try to do subitizing for sure?
All right. So when I showed this everybody, and if I asked you, what do you see? Most people would just say 3 trees, right? Also, most people wouldn't count when they did that. So it's an often neglected topic in early mathematics. Actually, then we hardly ever do it in primary grade mathematics, but I will argue that it's just as important through the grades, that we want kids to recognize and then subitize, which is just comes from a Latin word that means quickly or suddenly, the number in a group without counting. And so here's the Learning and Teaching with Learning Trajectories, or LT Squared website. This is subitizing right there. There's many, many topics that are important in early mathematics. But if you click on that button there, it opens up. And then if you click here on Learn About Subitizing, you see, unfortunately, a video of me explaining it in some text and other things like that. Then, if you want to see the developmental progression, those are those levels of thinking below. And I want to emphasize what Julie said, but didn't really focus on too much. Our levels are not small skills that are incremental. Our levels are broad patterns of thinking that include concepts, problem solving, conceptual growth, strategic competence, and the like. Anyway, we're going to do a whirlwind tour of this. We can't go into details given the time constraints, but trying to give you a picture of it and how we connect it then to instruction. The developmental progression goes from birth, seriously, all the way up through primary school, but it's got many levels. You probably saw them in that picture, but 4 broad categories can kind of encapsulate the forest instead of the trees, so to speak, of these levels. It goes from the approximate number system to recognition of number that's not necessarily quick for kids. They can't form the mental image and remember to attach a number word to it, but they can, if they see it, name a number. On to perceptual subitizing. the word subitizing is a hint that this is now very quick for kids, automatic. And then conceptual subitizing. So let's take a little video given to us with permission by Elizabeth Brannon and Libertas. They have a cognitive psychology laboratory, and they want to know, do kids really differentiate between sets of things that are of different numbers? So what you're going to see is that star in the middle above the baby there is going to focus the baby's attention. And then we'll see two rectangles on each corner of this that the baby's looking at. And the baby looks left, and then the baby looks right, and the baby looks left, and the baby looks right, and then the baby looks left and stays there. Because you can see that even though the dots are changing in size, arrangement, density, only the left one is changing in number. And yet the baby is a little scientist. And the baby gives the other side a chance. So watch his eyes, and he's going to look over there, and nope, boring. He goes back to the one that's changing. And it seems he's not only interested, but a little bit excited by this, right? In fact, it looks like it makes him happy to just be viewing those changes in number. And yet, again, as a good scientist, he says, hey, how about you? Are you interesting? And then he says, nope. So what we know from research like this is that kids are sensitive to a change in number from birth. This is something that we have gifted to us by evolution, and it allows us to start building mathematical competence virtually from the first months of life. Julie, who's this?
So this is our little guy, and we're trying to show you here is a way first into number isn't through counting. It isn't teach children how to count and count the objects. It is through the subitizing. And after we know we're sensitive to number, that's the beginning, then children learn to name sets. They recognize sets. They recognize this is 2, 1 in each hand is 2. This little guy just turned 3, and we asked to show us 3. Go ahead, Doug.
Oh, sorry.
What?
Try again.
Okay. Can you show me a different way with your fingers? Uh-huh. Uh-huh. Yeah. Yeah. Okay.
He
Thank
knows
you.
what 3 looks like. He's not counting 1, 2, 3 each time. He's not going 1. He just knows what 3 looks like. And that's so important because that is what's going to help him understand the cardinality principle, which is that last number word tells how many. It's understanding like this is what 3 looks like, and then this is what 4 looks like. So at the beginning of subitizing, children are able to name a set or give you that number without counting, but it's right out there. They have the perceptual support. The next level of subitizing, it's not there for them anymore. Show them, Doug.
So this is for you. So watch the screen for me for a minute. Actually, for just a second. And you all know that, of course, was 4. That's perceptual subitizing. Even if you don't have time to count, you're neurologically actually programmed, like the baby, to have separate neurological kind of sections that are sensitive, that respond to different numbers. And we've learned to attach number words to those, right? Then what's the difference for conceptual subitizing? Well, watch the screen again. That's this. And all of you could say, well, 8. But the reason we know it's 8, and they do EEG kind of studies on adults, that they can tell you, you can't see 8 all at once. It's too much to take in. You can see 3 and 5 and just immediately put it together. In other words, most people don't see 3 and 5 and then say, wait a minute, 3 plus 5 equals 8. No. Within a couple tenths of a second, they put those together and know that that's 8. So that is the basic kind of thing. There's lots of levels from number sense, the approximate number system, down here, to the recognizer, to the little boy who we saw, maker of small collections, to finally perceptual subitizing to 4 to 5, then conceptual subitizing, and people, it goes all the way up to conceptual subitizer with place value and multiplicative thinking. That's why this is not for young kids only. In fact, Grayson Wheatley, Julie, you always talk about, he worked with what, a 5th grade class?
5th and 6th.
5th and 6th, yeah. Other things on the website I'm just sharing real quick here. There's a focus tool up here, and you can pick a grade up to, again, birth, up to 3rd grade, 8-year-olds or so. And whoop, let me go backwards and show you. If you then pick a level, you go to a different page. This is not the website for time constraints. I'm just showing you static images. But you can see a level, you can read about what that looks like, and you can click on the
Look how it just
I think
quick moment. I like it at telling how.
going too fast for myself. Sorry. Here we go.
Without counting, just make a guess. How many frogs do you think I have here in my set? 5. 5.
Okay.
How would you?
Perceptual to 5. Then you can move up if you want to and say, well, what would it look like conceptual subitizer to 10?
Look how it just for a quick moment. Okay. I like it at telling how many grapes there are in this pie. Doing the grapes. Ready? Just for a quick moment. Grapes.
10.
Good girl.
I wasn't even counting because I knew it was two 5 makes 10.
That's right. Well, you've learned a lot, haven't you? Now I'm going to show you a card with some pennies on it. Try to tell me how many pennies are on this card when I show them to you just for a quick moment. Ready? Ready.
15.
All right. So,
I'm the smartest kid in my class.
okay, confidence is a good thing. I hope you could hear her. She was saying, I'm like the smartest kid in my class. Interesting. Why do we say conceptual subitizer to 10? She got 15, but she didn't subitize 15, did she? She took 2 5s and she knew that was 10. She immediately recognized there was another 5, but had to count on. But the wonderful thing about that, she'll learn conceptual subitizing to 20 eventually, but she's 4. She's 4 years old. The wonderful thing about that is it shows that counting and subitizing are both important. We say subitizing comes first because it does, but we don't. We love counting. It's the first and most basic algorithm kids ever learn. But here is an example that powerful thinkers who have been experienced high quality mathematics instruction put subitizing and counting together. I don't know what another 5 is over 10, but I know how to figure it out. I'm going to keep track with my fingers and count up 5 more, 11, 12, 13, 14, 15, 15. So they're complementary topics. What about this, Julie?
Guys, before you move on, can I interject a bit? The perceptual subitizing that you're talking about, does it have anything to do with photographic memory and stuff?
Oh, interesting. Go ahead, Doug.
No.
No, it's really interesting. But how can I put this? If you're good at it, you see that you experience the quantity without necessarily seeing the image exactly of the quantity. So if I see, I wish I could show you like a really big number that it was, but it was like tens bundle, tens bundle, tens bundle. And you're like, okay, 33. you're not actually like taking a photo of 33 and like then counting it or whatever. It's that you understand the quantity instantaneously. Doug can talk more about the neuro aspects of it, but Doug will say that you when you see a quantity like he saw 7, you see 4 lights up, 3 lights up, then 7 lights up, and it's instantaneous and unconscious, but your brain's still doing work. So it's not as much a pure picture. It's still a process and
Oh,
not
okay,
a
okay,
static
okay. So
image.
it's not so much as just slapping it in, but still an active uh,
Yeah.
addition and whatever process going on in.
Yeah. It's super fast and unconscious.
Yeah,
But
consciously.
it's like if you're good at quantity, again, most of the people here are going to understand quantities and be good at quantities. I can right away say to you, all of you, I want you to think of 13 and you'll think of it different ways. You can see, I want you to visualize it. You'll be able to visualize it, and it's almost hard to stop thinking of all the ways because your brain just gets generative. Young children who don't have that really have a much tougher time with arithmetic. And so what we're trying to do is to build up that ability so that they can not only works with counting, so that they understand what 4 looks like and 5 looks like, but that they use it for arithmetic later on. Go ahead, Doug.
Also, what you guys are saying sounds familiar. Some years ago, or maybe it was in the 70s or 80s. I'm not sure. They used to say that babies are able to perceive beauty right from birth.
Yeah.
Yeah.
Yeah, symmetry, right? That was the
Yes.
research on symmetry, I think, right?
Yeah, correct. Yeah, symmetry. Yeah,
Yeah.
right. So that the way you are saying it looks like the supertizing is already built in to all of us.
Yeah.
Okay.
Yeah, no, when we say subitizing, we only add the thing that for us as mathematics educators, the sensitivity to numbers built in, the ability, of course, to name the numbers and then to start processing them comes with experience and learning. So not everything is built in for sure. We like to say theoretically it's an interactionalist theory that understands that there's nativist competencies that come, and then you still build on those through development. So we try to match the teaching, right, Julie, to the level of thinking of the kid, where if they've attained this level, then our target, those of you that know Vygotsky will be familiar with the old zone of proximal development, is the very next level in the learning trajectory. Did you want to talk about any of those, Julie?
No, there's a question in the chat about grouping versus in a row, etc. The research is actually interesting. People color in, you don't want to use color, you want to do solid items that color doesn't determine what you see. Doug, isn't it up to 4 in a row or 5 in a row?
4 in a row. If you want to know the research on the easiest to hardest,
Yeah.
4 was easiest for perceptual. 4 vertical is next up to 4, right? Not 4, but 1, 2, 3, 4. Oblique, and then come the patterned arrangements, such as a square for 4, the corners of a square or something like that. And then as people develop, it's pretty interesting, to me at least. 2 rows is a particularly good thing for even numbers, as you can imagine. And then other arrangements are better, like dice patterns, like a 5 with the square corners and then the dot in the middle of that, are easier for odd numbers. But at that point, once kids are looking at these different arrangements and all, it's all good. Whatever, if it's a little harder of an arrangement, who cares? We want kids to be able to recognize different arrangements. Indeed, I don't have these slides, so unfortunately, but oh gosh, I'm blanking on her name, Julie, the California person who wrote that chapter for our book, said she taught her kids the dice pattern for 5. I hope I'm making sense to you guys. It's square corners and dot in the middle. And then she just kept teaching them that, and they all could say 5. But when she had them draw it, some kids made an X out of 7. Some kids made different arrangements, like just a square, but left out the middle one and thought it was 5 because she hadn't used different arrangements. So a variety of arrangements at the beginning of, like Julie said, high contrast items is a really important thing to include. Once kids are up to subitizing up to
Kathy
10,
Richardson.
Kathy
Sorry.
Richardson.
You asked me a name and it took me that long for me to think of it. Once I got it, I was like, Kathy Richardson.
I
Yeah,
still
Kathy Richardson.
come up with it without you. Once kids are subitizing up to 10,
This is
it's
stuff.
no longer necessary. They understand totally the quantity and they have mental models. So we go to 5 and 10s frame. Some people just call it a 10s frame, and we do a lot with 5 and 10s frames rather than a lot of different things. So we play games like that. I don't know if you even want to mention an early one like Tricky 2, Julie, or you think we're out of time.
We're out of time.
So I will do a couple more subitizing and then we're going to go right to the end. It's not for the young. Here's a interesting study where number system knowledge discussions that they had when they did this in 2nd grade, when they did these, and they did some interesting arrangements like this. Think about this, people. This is pretty interesting because you tend to see 9 and 1, right? But look at this one. If I flashed that in front of you, would you know right away how many? I mean, many people think, I got it. If it was 9, 3 rows of 3, you took out the middle one. But many people try to say, oh, it's 12. Well, wait a minute. How'd you get 12? Because 4 sides, 3 on each side. Whoops. Kind of double counted the corners there. So this really helped kids on all their math, including arithmetic, at the end of 2nd grade to do this, because they start developing mental models. This is not an instructional diagram. This is what we want kids to be able to do in their minds. Is I ask you 8 plus 5 when you're kindergarten, late kindergarten or 1st grader. And you can say, if I move these 2 over here, I can see what I have. And Julie already mentioned we do things like, I think you said 32, Julia. This one's 24. So that's I'm going to skip down way to the end. Skip the research, Julie. Do you want to do bajillions or?
That sounds good.
Okay, talk to them about bajillions a bit, and then we'll
So
conclude.
bajillions is just like, reason why we bring it up is because we're scientists, right? We're always trying to do research and develop things. And I think what we've talked a lot about is how our research is continually evolving and we're synthesizing the research of others. This is our latest project, so it's more the cutting edge of our research. But what we're trying to do is to find a way to get this information into the hands of more people in an easier way to do format. So rather than meeting with us and doing lots of professional development and having in-classroom coaching, people just need their phones. However, they do need to interact. So the phones will allow, or an iPad, children play some games, and the games use pretty complex statistics to try to figure out exactly what level along that learning trajectory they are. And then they give that information to the teacher in a way that says, we would say, like, if a child's lost, the first thing, if Doug calls me up and says, I'm lost, I say, where are you? The kids playing the game will let the teacher know where they are. And then they can meet the child where they are and help them grow mathematically. So it gives suggestions over what to do. It teaches them a little bit about the children's development. But with teachers being so stressed right now after the pandemic, I don't think an educators ever really came back. This felt like an easier way. It was a response by a call from teachers to say, we're really not in a state where we can take in more information. This is a way to get them to take something off their plate, but still help them to understand children's development. So we use hands-on activities. We invite them to learn more about learning trajectories. But if kids just play the app, it's okay for a little bit. If you skip a couple weeks and kids are just playing the app, that's okay. Your kids are still going to progress, and you're just going to learn more about your children.
Well,
I think that's about it. And there are questions. It's time for questions.
That's time for questions, yeah. Thank you, Doug and Julie. That was very refreshing. But I would like to ask this. Much of what you said seems targeted towards changing adult mindset, more for teachers. Is that correct?
Yes.
No,
it's about talking adults, because the way adults create mathematics for kids is based on normally adults' way of understanding math and not understanding and respecting children's way of math.
There's one in the chat.
Yep. What is the best age for exposure to algebra? Well, that depends on what your definition of algebra is. I mean, if we start thinking about that, the earliest pattern that kids learn is +1, right? +1 is an interesting, very interesting pattern that is algebraic in nature. So if we start doing +1 really young, I would say that for us, if you wanted to think more traditional algebra, the idea, one of our earliest games we do is Guess My Rule. Would you say, Doug, that would be it? Guess My Rule?
Yeah, that's a good example.
Yeah, or like function machine. It's a function machine thing. And Doug, you did that with kindergartners, right?
All the time. Yeah, they love Guess My Rule on function machines. Yeah. So, online it's easier. I actually built a function machine with little cards that you'd insert, and you would insert a card 2 and it would come out 4. You would insert a card 5 and it would come out 7. And they would play that again and again and then try to guess it. So I'm putting in a 10. I bet it's going to be 12. How did you figure that out? It's always 2 more. It's like 2 counts more. So, this is basically x plus 2, right? Y equals x plus 2 in a very developmentally appropriate and cognitively appropriate form for those kids. So we do a lot. A mathematician called Lynn Steen, half a century ago, defined mathematics as the study of patterns in number and space. So he didn't define it as knowledge of number and space, the study of number. He said it's the study of patterns in number and space. And of course, the study of number led to algebra, and the study of patterns in space leads to all kinds of measurement geometry and the like. So we believe that these kind of foundational things are at least pre-algebraic in important ways. And certainly
Right.
in our first and second grade stuff, Julie, we're asking kids to do things like, what's 14 plus 7 equals blank plus -7 or something, and how do you know, and how did you figure that out? And eventually, is A plus B equal B plus A, that we actually use letters and things like that to get at that kind of pre-algebraic knowledge.
So there's a question in the chat about from Thailand. Thank you. In addition to learning trajectories, what competencies and pedagogical content knowledge are essential for preschool kindergarten teachers in teaching early math and integrated STEM education? So the idea is what do teachers have to understand, not just how to teach, not just the math, but how that interacts is the key. What do children understand? And if you don't understand the math, then you can look at what children do and really not understand that either, right? It does require a synthesis of understanding content, understanding teaching approaches, and understanding children in order to really do good integrated STEM education.
Julie, maybe give just a a really quick picture of when we work with teachers over time, how you set that up to do both the math and the development and the teaching integrated.
So what we've done is we talk about the math, we engage in the math. So say there's an area like measurement. Measurement is something that a lot of adults get through and don't really understand. Even basic length measurement, units and things like that, they don't understand. And definitely area and volume is things that a lot of adults just really don't, they know how to line up a thing and write off a number, but they don't really understand it. So what we will do is ask them to actually engage in some math activities and reflect on their own thinking to start. How did you think about this problem? What were you thinking? And then we'll give them a task to do with children, where they watch children do a task, obviously an easier task, and they learn information about the children. Then they watch videos and things, and we talk about the developmental levels of learning trajectories, and they're able to say, all right, where are my kids in this? How do I make sense of what I'm seeing in my classroom with my children in this framework? And then the last thing is, okay, what were you normally going to do to teach them? Let's think about where that activity is targeted to development. And if it isn't targeted to where your children are, then how are we going to adjust it so that it does meet the needs of your children? So it's an extended process where we try to tie all the pieces together.
And by where your children are, Julie, always means where your children are ready to learn, then the next level beyond the level they've already attained. Although they're always working on multiple levels at once. It isn't a lockstep kind of
Essentially, that was going at teachers the way you would go at the kids themselves.
Very much.
Teachers, yeah.
Yeah,
Right.
yeah, exactly.
Okay.
And go ahead, Doug, you wanted to talk about the thematic. The problem in early childhood is all STEM is lost for the theme, right? I had a teacher, I'm like, what are you going to do next week? She says, oh, we're going to be building towers because we're doing a unit on castles. And they're going to be building towers. And I said, so what are the math they're going to do? She says, I'm going to have them count the tower. I said, how high do you think they're going to count? Oh, probably they'll get like 10 blocks high. I said, do they know how to count up to 10? Oh yeah, they all know how to count to 10. I'm like, then why is that your goal for math for next week? Because we're making castles. So we had to talk about how could we tie in the mathematics of the children into the theme rather than let the theme dictate the content. Too many times in early childhood, the content is determined by the calendar or the theme, and really isn't honoring where children are developmentally. That was my 2 cents, Doug. You want to?
Okay. Let me stop you there. The problem there is where does the preset syllabus fall in all this? That is going to go at loggerheads with what you just said. What you just said is the teacher has to be perceptive towards kids' development and react accordingly. But
Yes.
how does she fit herself to the kids and to the system?
The system have to be looked at in the bigger picture. That's the goals, right? So she still can help children meet their goals. She has to keep those in mind, and that's where I want all my kids to be. At some point during the year, they're going to meet their goals. But if they meet their goals early, then to just say, "Oh, good, you get a gold star, go play," that's not meeting the needs of the children. I need to extend them, right? I need to challenge them. And if a child's struggling, I need to still meet them where they are. We have plenty of research. We're teaching kids according to the goal, right? So I'm going to show you how to do the goal over and over and over and over again. So we do one group, that's what you do. In another group, we say, okay, they're not there yet. I'm going to do with where they are developmentally and bring them up. Which group does better? Well, hypothetically, it could be either. The one group gets lots and lots of practice modeling that one type of problem. So they might do better. The other group gets more support. They're going to make sense of it. Well, sure enough, the group that got more support and made sense of things outscored the children who got lots of time practicing. So if we always take into account the children first, the system, keep in mind where your goals are. I'm not saying ignore it, But if in this case the children knew how to count to 10, making that, it's just silly,
Yeah, and I hope people remember those were the studies we talked about when we talked about
Yeah.
compared to teach to target.
Yeah.
There's other people have done those studies, but Art Baruti, Julie, and I did a bunch of those, and they pretty consistent findings of along the lines of what Julie just said. The other thing about thematic kind of thing, so what do you do? All Julie's saying is it's great to integrate what you're doing in mathematics into the theme if that helps the theme and helps the math. But it's the latter thing that Julie was worried about there. So, like if you have a game, like we have a game called Cookie Game, and we encourage people, if they go visit an orchard, make it an apple game. Change the thing but keep the same mathematical goal. Similarly, a lot of people in the US in the spring, when people are planting, they'll grow little, they'll grow seeds in a little cup, a dirt cup, and watch the seeds grow. And it's not atypical, even in kindergarten, for kids to be asked to count the seeds that germinate. That's counting to maybe 3 or 4. For our kids, it was usually 0. So maybe they learned something about 0, but anyway, they'd count a small number. What Julie and I did is said, yeah, they can subitize that like that and tell you, but that's not the math lesson. So if you're growing flowers, how about this? How about we compose a whole diorama of flowers that are made with either pattern blocks or tangram shapes that kids compose and make up their own artistic flowers, and they're learning shape composition at the same time. Then you're at the cutting edge of the child's learning and development, and you're still in with the theme, but you're doing something important mathematical. So integrating those two, sure, try to do the theme whenever possible, but make sure that the math and the learning of the kid is of premier importance in how you integrate the math into the theme.
You want to answer Carrie on the chat from Hong Kong?
I think we were.
No, I think you did that, Julie, right?
Yeah.
Okay. All right.
Yeah. It was talking about theme and
Yeah,
trying
sure.
to
All right. Okay.
change the content.
Yeah, sure. So tak ada lain. Facebook ke apa tak ada. Suppose that's about it. We had Carl Wyman on STEM a few months ago as one of our speakers. How do you compare your findings with his?
I'm sorry, I didn't catch that.
Carl Wyman on STEM.
Don't know his work, so sorry.
Oh, I don't know his work. Okay. Carl Wyman. Weimann.
Yeah, he's a physicist at Stanford.
Yes.
Yeah.
Now
we do completely different work, right?
Yeah.
So what Doug and I are doing is we come from an educational background, right? We're and we have colleagues who are brilliant mathematicians and scientists with whom we consult. In fact, they're the ones who originally help us think about what are the important goals mathematically. But I think what we do that's completely different is, again, take the work of psychologists and cognitive psychologists and math educators, and we try to synthesize it so that we're focusing on what's happening in children. So it's not just about the content, which is amazing, and you need those people on your team to help figure out the important nuances. Like I said, if you don't understand the math, you can't do this kind of work either. So it's very important to understand it, and brilliant people like him who do understand it are necessary. But Doug and I are coming from what is the children's mathematics? What is the children's understanding of the world? Carl talks, he's a physicist. That's wonderful. We do work in STEM, and we have built these learning trajectories.
Carl,
Yeah.
I didn't hear
Yeah, we built these learning trajectories for birth through age 5 in science and math. And like here's something that's really interesting. So light, right? Light. It seems like children understand light. How do they understand light? That's really interesting. So we investigated how children understand light. They don't. Not till age 5. They really don't understand light at all. And of course, it's an incredibly complex concept, light. I mean, they have an intuition, right? There's the light, there is light. But if I make a shadow, we thought, oh, it's fun for kids to play with shadow. But when we showed them a book with shadows of animals, they thought that the shadows of the animals were additional animals. So there was like a fox and a shadow of a fox, so 2 foxes. They didn't understand that putting something in front of the light caused the shadow. The shadow was its own thing. And understanding that is amazing. And that's the kind of thing that Doug and I do, which really helps inform our colleagues in physics. So our colleagues in STEM help us inform us about what are the big ideas and how do we understand them. And we do the work with sitting with little children and watching them and observing them and inform the field of how children understand the world, if that makes sense. So we're coming at it from 2 different ways, and hopefully we can all get along and collaborate. And I think we do. Like I said, Doug's great at that. Doug has a listserv with a whole bunch of mathematicians that he's in regular email communication with. I'm not allowed on because I'm a woman.
They have women, but the women.
There's one woman.
One woman, but she has to be a mathematician, not a man.
Okay. How far can you take this concept of yours with children age?
What do you mean?
Do you stop whatever you're doing when they're 5, 6, 7, 8, 9, 10, 15, 20?
We do this up to grade 7 or 8 just because that's typically defined as early childhood education in the United States and many other countries. But Jer Confrey, Julie, has at least taken the learning trajectories approach, at least in some fields such as multiplicative thinking and fractions, right up into middle school. I know that you mentioned physics and science in high school. Dr. Liu from University of Buffalo has developed many learning trajectories for chemistry, magnetism versus electricity, and other kind of science topics. So I really do think it goes all the way up, but is not as well developed. Julie and I, she said, we stand on the shoulders of giants in developing the learning trajectory, right? But we had the advantage that people love to study young children early math because math is well defined and it helps you figure out the kids' thinking. So it's not just math educators research and early childhood educators research, but we get cognitive psychologists, cognitive scientists, educational psychologists, and neurologists. Like we showed the video of the approximate number system, all doing research on young children and learning math. So we had a lot of help. It's going to take, I think, more and more and more work to extend that up, but there's no reason it shouldn't be.
All right. Before we go into the chat question, can I ask this? You showed a number system of dots for addition, subtraction, whatever. How different is not how different, how effective or not effective are dots compared to the subjective symbol of 7 or 8 or 3 or 13 or something like that? The numbering. How do these contrasts compare?
Yeah, eventually those two come together to use the same kind of thing. But for sure, the dots early on is an actual quantitative model that activates neural patterns that come from evolution way back, so that somebody could, like before people were naming numbers, they had evolved to be able to know that a group of 3 animals is more likely to yield a better dinner than a group of 2 animals, So those kind of either dots or objects or something like that are essential to jumpstart this kind of quantitative notion. But as soon as kids start attaching a number system to it, that starts actually then activating the same neurological pattern. So they become very effective. Research out of the UK shows that knowing your numerals really makes a difference if it's not a rote enterprise, but is a symbol for quantity. They're used by kids. It's reasoning. I think we all know that what we don't want to do with numerals, though, is start routinizing it, making it trivial, so that kids see numerals when it's 3 plus 4 equals, and then there's a blank. But if you give them the problem 3 plus blank equals 7, they don't know what to do with it. No, the answer's supposed to come at the end. So when we do numerals, we have to use them as flexibly and in mathematically interesting ways. So kids see problems such as 7 equals 3 plus 4 as much as they say 3 plus 4 equals 7. And they also say 3 plus 4 equals blank plus 7. And they have to reason out what would go there. So they get the idea that the equal sign isn't the answer comes next. The equal sign means equality, balance between the two sides. So I don't know if it address your question.
The question in the chat says,
On
how
chat,
do you
yeah.
help 19-year-olds to catch up with lower secondary math quickly? I mean, it depends what the problem is, but it sounds like if they really don't understand stuff, our research would indicate that the best thing to do is to focus on what they don't know and to help them understand what they don't know, even if it's like, oh no, I have to stay with the class, I have to keep doing this other stuff. If you don't spend the time so that they really understand that lower level secondary math, they're not gonna do well ever, even if they can pass like a quiz. I used to tutor to make money in high school. I used to tutor people. I could get somebody to pass a quiz just by memorizing for a night and getting it done, but it doesn't work, right? So if we really want to make a difference, we have to really help them understand that lower secondary skill, and they'll do it quicker. I mean, it might not be very quick, but they will get there, and they'll do better than if you just keep trying to get them to memorize so that they can stay up with their peers. I know it can be discouraging, especially when you're talking about a 19-year-old who doesn't understand math. But I promise you, it's time well spent. And if you do, and they really things start making sense to them, they're going to feel much better about themselves in mathematics.
It's 19-year-olds all the way down to 8-year-olds, Julie, who don't really understand what a fraction is, for example, right?
Right.
Really important kind of understandings like this. And you can't just teach them routines for finding the lowest common denominator. They need to understand that a fraction is a number. It's not 2 separate numbers separated by a bar or something, Very important.
Okay.
Thank you for having us. We really appreciated it. This was fun.
We have a Dr. Othman Talib. Doc, do you want to ask anything? Dr. Othman? Dr. Othman Talib? Any questions from you? I suppose that's about it. Guys, thank you very much for enlightening us on this very, 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 very important topic, future of our kids. Before we move, we say good night to you guys. I would like you to I would like everyone to switch on their cameras so we can take a group photo with both Prof. Douglas and Prof. Julie on this very important topic. Hope everybody can switch on your cameras. Yes, please. Thank you. Cameras, please. Cameras. 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 Muhammad Azrin, Ahmad Zarif, Amirul Islam, Prof. Cameras on the other side. All the cameras are off. All the cameras are off on the other pages. Please, everybody, cameras. I'm not selling cameras. Wait. Okay, Ida Hashim. All right. Apa nama dia? Are we ready? Can we take the pictures? Can we take the shots? Can we take the shots? Thank you. Keep on. A bit more. Yes.
Doug.
Okay. All right. Are we done?
I think we're done.
We're done? Okay.
Thank you so much
guys.
for having us. It was
Thank you.
lovely.
Thank you for gracing our place with your presence. We
It was
appreciate it very
lovely to
much.
see you.
So
Take
lovely
care.
to see you. Good night, Prof. Douglas, Prof. Julie.
Thank you.
Good
Bye-bye.
night. Bye. All right. Thank you guys for joining us. Our next Isaacs will be 17. Oh yeah, there's an attendance QR coming up soon. For Unimap je kan? For all, okay. You'll get an attendance soon. Where's the attendance? Mana? Oh, okay. Yeah, you can click on the QR code for your attendance sheet, please. Thank you, guys. Thank you. Have a good day. Salam sejahtera, and bye-bye. You'll get an e-certificate. Guardian tak payah kot. Hari Raya pertama gemuk lah. Apa lah, cik. Otak.
Pendek dah. Kenapa kau kamera dua tadi? Nampak amat dua kan? Mentang jual kamera ada dua.
Dua kamera. Okay. Alright. Thank you guys. Bye-bye.
Okay.
Thank you, Chris. Alejo. Where are you from? Chris. Vallejo. Oh.
Aku nak tengok tempat
The QR is on now. The QR is on the main page right now. Ida Hashim. Can you see it? The Sensor Nano page. Thank you. Okay, bye. Thanks for joining. Prof Hosman tak mau jawab tadi.
Di belah apa? Tadi kita tengok dia cakap Facebook dia dia ni.
Oh. Okay, there's a Google form on the chat also. Okay, bye-bye. Good day, everybody. Salam sejahtera. Terima kasih.